The what? You mean these redox systems, how the chemistry is? Some of them are very simple to make, yes. Actually, my postdoc, Jochen Friedl, who has originally even done his PhD with me, he's a physicist. And so what's the knowledge of physicists for chemistry? Pretty low, right? And he looked into this, and then he started making them as a physicist. So that shows actually how simple it is to make. And I asked him, it's just your curiosity? No, he said, okay, you take this and just put it together and stir it for a while, and then you have it. Actually, then it sort of precipitates, and then you filter it off, and then you dissolve it in some other material, and that's okay. So it's not complicated. Of course, maybe in the end, some of the compounds that are especially good are a little more complicated to make. I don't want to say this, but in principle, it's not a chemistry that is really inaccessible or so. Yeah. No, it's not very complicated.
Yeah. So you mentioned that the chromic efficiency is 98%. How about the voltage efficiency, the energy efficiency?
Now, I mean, when you go to the coulombic efficiency means that I, let's say, reduce a component and oxidize it again, and how well does it work? That means how many side reactions I have. And that is actually very low. I mean, the efficiency is very high. The voltage efficiency depends very much on the construction of your cell, because you have a current flow and you have some ohmic losses, and that goes into the voltage efficiency. And it just depends how well you work actually your cell. But when you have a coulombic efficiency of close to 100%, probably your voltage efficiency will be, with an optimized cell, above 90%. Yeah, you just. Vanadium system is not very. Actually, vanadium system has one big problem on the negative side. The vanadium-2, vanadium-3 is when you go actually to negative potential, it starts to overlap with hydrogen evolution. And then the hydrogen evolution, of course, reduces the coulombic efficiency. And so the overall coulombic efficiency is, I think, around 70% of the vanadium cell. I think on the positive side, there is not so much of a coulombic efficiency, but the problem is that the kinetics of the positive side is very poor. Exchange current intensity is very low, actually. There's one graph. I've quickly scanned over this, but oh yeah, here. So you see, this is the vanadium 4,5, and this is the vanadium 2,3. And here is the rate constant. I don't know why it's written twice. Anyway, this is a rate constant plotted here, and the difference between these two vanadium reactions already is about 2 orders of magnitude in exchange current density or rate constant. And the problem, of course, is when one is limiting, it doesn't help very much when the other one is good, right? So the whole battery is then determined by the slowest reaction. Right. Yeah, I mean, you can do this to a certain extent by having larger electrode surfaces, right? So that's what you do also. You increase the size of the area. But this is exactly another problem of the vanadium cell. So what they use as electrodes are carbon felt electrodes in order to have a large surface area to compensate the bad kinetics. But the felt is a flow resistant to the electrolyte, because you have to have the electrolyte flow through the electrode. And this flow resistance then requires actually pumping, and then the pumping energy goes away actually from the overall efficiency of the system. So there are a number of factors that are not so positive. What's positive is, that was one of the reasons of choosing actually the vanadium, is whenever you have actually some leakage through the membrane, there is no chemical contamination because it's always vanadium, right? So that's a big advantage. But we have seen that these large ions are also no problem because they just don't go through the membrane because they're so large. They're about 1 nanometer diameter compared actually to few angstroms, 2 angstroms or so for the metal ions themselves. And so the danger of crossover is not very large.
So how does the real electrode look like? Is it just platinum electrode, is solid, or is something like metal bridge?
You mean for the mega ions or for the vanadium? No, the vanadium uses carbon felt in order to have a large surface area. So they use actually carbon felt electrodes, and then of course they can't use very high current densities. That's also the limitation of the power, because then the ohmic resistance in the carbon felt would be too large, and then you have too many losses. So there are a number of things that are not optimal. But when you have a high kinetics, then you don't need the large surface area, and you can draw much higher currents for a flow system, let's say, and you don't need actually this flow resistance, and you can have actually massive electrodes that don't give you an ohmic resistance also. So the flow resistance and the ohmic resistance can be reduced.
About the PVI system, so because you are running is already at about 160 or 230 degrees Celsius, but the performance is even worse than the 10 pure cell at the moment, and then the platinum loading is not low at all. Still 1 milligram more gram per centimeter, or 1 milligram.
Yeah, that's a little bit the problem with the phosphoric acid, right? Because the phosphoric acid, especially on the oxygen side, absorbs on the platinum catalyst. That's also a problem that the phosphoric acid fuel cell had, and that requires then a fairly large amount of platinum. Yes. Yeah.
So then that is that. So has anybody tried and maybe use something offset something like use some solid acid instead of phosphoric acid to build the?
Yeah, but that's essentially similar to the approach we are taking with the APP, because you have a proton conductor in the solid state. Then you don't have that problem, right?
Yeah. Is there any other successful result instead of the APP and
Yeah, people are working actually on some also some hydrates of inorganic salts that have a proton conductivity. I think cesium sulfate hydrate is a material that's being considered, and some other materials. Yeah, they're sort of. But so far, it's an experimental. It's still in the experimental stage, actually. Yes.
So about performance and stability, is it still promising?
I mean, what we have actually studied, that stability looks pretty good, actually. Performance, we have made actually one fuel cell that looks also pretty promising, but we haven't actually sort of developed any electrodes that can work at, let's say, 250 to 300 degrees, because the electrodes we have used were actually from high temperature PEM, so you're restricted to 150 degrees. Or 160 degrees. So there's still some work necessary. But so far, it's quite promising, actually. So one just needs to keep working, actually, on it. Yeah. And I also think that you need to have actually new supports for the catalyst, because you can't use carbon for these high temperatures, because the carbon corrodes, actually. But there are possibilities in using metal oxides like titania, reduced titania that has a good electronic conductivity, or reduced tin dioxide has a good electronic conductivity. So there are a number of possibilities, and I think they all look quite promising. Yeah.
So have your group ever tried to reduce the dioxide?
No, we haven't done it yet, but I know other people have done. It has been published actually. Yeah, that looks quite good, and they have stabilities then up to typically 400 degrees. What is an issue for using reduced metal oxides is when you go to the cathode, because when you have this at higher potentials in an oxygen atmosphere, then you easily have a reoxidation of the metal oxide, and then this may actually lead to some higher resistance than of the material. So that is definitely a point that needs to be considered. But I know actually from some work that has been done with for titania with the mixture of carbide and oxide. So you have a mixed, it's like a TiOC or something like this. So where you stabilize the reduced state of the titania, so then you potentially have this actually stable also at an oxygen atmosphere and higher temperatures. Yeah, it's a question.
I had just been curious about one thing. When you talked about the solid oxide electrolysis cells, the ideal materials for both sides of the electrodes were these rare earths. I was wondering if you knew why such to me it seems like a very exotic material.
That's true. It is sort of exotic, but you mean that it makes it expensive then in the end?
Well, yeah.
Yeah, potentially it does, but the total amounts are actually not that large. I mean, you are talking about thin layers of maybe 10 microns or so that are being used as electrode materials. So I think the total amount is not that large. I mean, you have more for the membrane. That's sort of this yttrium stabilized zirconia, because that's thicker. Typically, it's maybe there are different ways of making that. When you have a freestanding film, it's about 150 microns or 120 microns. When you have a supported film, then you can go down to a few microns actually. Like 5 microns or so, and then you reduce also the amount of material. I think the problem with the solid oxide concept is more, in terms of cost, is more actually the processing. That typically the processing, I mean the techniques that are being used, that they can be expensive. And I mean, I had a discussion actually with Bing Chi actually about from the company Green's G-Cell, and they have been actually using some sputtering techniques for making some of the layers, the cathode layer for instance, and then I asked him about this. Do you think that you can use that actually also for mass production, because it's not a cheap technique actually? And he said, yeah, we can. So, okay. And he did his calculation. But I mean, that is definitely an issue which one has to take into account. And actually, some commercial programs have essentially been stopped because of the high cost for fabrication. Not because of the high cost of the materials, but the high cost of the fabrication. I mean, for instance, you know, probably the SOFC concept of Westinghouse with these tubes, the tubular concept for solid oxide fuel cell, that then later went to Siemens. They took this over, and Siemens tried to sort of commercialize it and said no way actually, and then they tried to modify the technique. In the end, they gave up on everything. So the kind of fabrication techniques for mass fabrication is an issue actually with solid oxide. It's not simple. Tape casting is simple, but when you come to the thin layers, it becomes critical. Okay.
So it just mentioned that people can take the mixture of solid waste then to make ethanol. So is there already some successful plants operating in Europe or somewhere else?
I know that there are some sort of, I mean, not on a commercial basis, but actually on a basis to have at least a scale that is close to commercial. There are some factories or some processes running, yes. I know actually in the US there are processes running. I know in Europe there are some places, maybe actually also in China, but I don't know about China. I think China would be actually a very good possibility. Yeah, no, I think it would be good to avoid actually a lot of the problems you have in China. Yeah.
So, okay, 我的问题是，就是说，现在市里头其实有很多的生活垃圾已经没有这种工厂来做乙醇了。你们要是谁感兴趣的话，赶快去调研国外的这种工厂，然后自己找保证这建筑100万户，或千万户，应该是，这个100万户不是那个。Okay, this is one question. So another question is, so you mentioned that the Linde has bought some fuel cell car from Hyundai from the South Korea. So why BMW or Daimler Chrysler, they don't build this car and
No, I mean I think Hyundai was really the first company worldwide that produced a fairly large amount of fuel cell cars. They started what they call like a serial production of it. Although the series is small series, but at least they did this. Toyota has actually announced this for, I think, next year. And I know that Daimler and Ford were in preparation of a serial production, but then they postponed this because they wanted to have a larger amount of vehicles, because that reduces the cost then per vehicle. And so they joined forces with Ford. That was sort of the last information I had. BMW is not really active in, I mean, they do some fuel cell research. They have some time, I don't know, I think a few years back, they worked together with Volkswagen on the fuel cell. Volkswagen has done some research. But recently BMW rather joined forces with Toyota, because Toyota is more advanced actually in the fuel cell area. But if they, to which extent they will go for this, I have no idea. I mean, I think the concept really can be, but you have to move away from the hydrogen, is to have like small fuel cells in a car, in a battery car, that recharges the battery. And this way you can extend the range of the cars, because I think really a big issue is the limited range of the battery car. And if you can overcome this, that's good. I mean, the BMW has an idea about this, because this is the only company that offers a battery car with a range extender based on an internal combustion engine. So you can actually buy this battery car, the i3, with an internal combustion engine, which is actually a motor which they have taken from their motorcycles. And so even at a reduced speed of, I think, 60 kilometers per hour, at least you can get home. And you have a range of, I think, 200 kilometers or so. So that is something which I think is a very smart move, because it takes away the sort of the anxiety of people. Oh, when I drive a battery car, then maybe I get stuck and then I can't do anything, right? But then the more sophisticated way would be actually to put a fuel cell in there. And it's sufficient to have actually a few kilowatt. You don't have to have like a huge fuel cell. Just a few kilowatt are completely sufficient. We have done actually some calculations with about 5 kilowatt for a small car though. 5 kilowatt, you can actually go 100 kilometers per hour. So, my God, I mean, it's no problem, right? So you always can go home with, let's say, 60, 70 kilometers per hour, and then you need just a few kilowatts.
So, could you make some comments on the difference between the Toyota's Mirai and the previous new fuel car? So, which one?
Oh, actually, I don't know. No, I haven't really looked into this in detail. But I think I would assume, to be honest, that the difference are not very large. Because I think the technology in terms of fuel cell technology and then also the surrounding has been pretty clear actually. It's a long time ago already. People have done calculations how to set up the system. Let's say when you have a fuel cell system, you always hybridize that with the battery because you don't use all the power coming from the fuel cell. That's not necessary. Part of the power can come from the battery. And that's typically a 1-to-1 hybrid in terms of power. So all these things have been more or less worked out. So I would assume that the systems are not very different. I mean, details of course are different, but because that goes also back to patents and all kind of things, what their intellectual properties rights are, and that have the consequences then from selling something, right? But the principal solutions are very similar, I guess.
But then Linda prefers to buy this fuel cell car from Linda, not from Toyota. It's just
yeah, because Toyota has not, it's not available from Toyota yet.
Oh, at that time.
Yeah, no, I mean, Hyundai was really the first company actually to, and they used that even to promote their idea. We are the first company in the world that produces fuel cell cars as serial cars. So, and Toyota actually planned to, I think next year or so, they want to have a serial production.
A lot of cars sold in the year, maybe already 2,000 fuel cell cars sold in the year, maybe in California, because they have high
I think that's right. Actually, a lot of them go to California because California has a very strict emission control, and I think they have a lot of incentives to use emission-free vehicles. And I think most of the battery cars are currently also in California, actually. And it's no surprise that Tesla is actually coming also from that area. Right?
Okay, I guess we are waiting here. They want you to give us some information about how this professor is so successful in
yeah, but that's difficult. We had some quick discussion at lunch already on this. I mean, that's difficult to say. There are not recipes, right? But one thing definitely is, and that's what I mentioned already, is you need to be curious. If you're not curious about how things are, I think you don't have the driving force to go through all these processes you have to do when you do research. Because a successful professor is actually one that, of course, is also able to teach successfully, but I think the teaching has to be fed. Sort of the nutrition of good teaching is actually having good research going, understand the research, understand the processes, and doing good research comes from having a clear mind but being especially curious. I want to solve a problem. And when things are difficult, I don't get discouraged from difficulty, but I keep going. I have the goal, I want to solve that problem. And that's extremely important actually to keep this in mind and keep working on this. Then you are able to be successful, because then you actually can come up with solutions in the literature and publish your work in good journals when you're actually at the forefront of trying to solve problems that other people have not solved. Rely on literature when you want to know what the status quo is right now in understanding, but rather ask the question, what are the problems that have not been solved yet? And go for that and try to use unconventional ways of answering this, and not the same way as people have done before, because these routes are often then the routes that are not so much successful. The unconventional way may be actually the more successful one, but at the same time it requires that you are really curious, that you want to have a solution to the problem. That has to drive you. And you have to think about this not only from 9 to 5 during the day, but it has to occupy your brain. Even in the evening, even when you're sleeping, you think about the problem, how to solve that. And also on the weekend. So then you have enough energy to really be successful in solving the problem. But the point actually that really drives everything in a way is curiosity. And without curiosity, you don't drive anything.
Could you talk something about one of your PhD students who later on cleared up the small fuel cell company?
Oh, Manfred Steffner. Yeah, I had actually one doctoral student, Manfred Steffner, a long time ago. He came to me actually. He was not a chemist, and he was not even a chemical engineer or something like this. He was a mechanical engineer, and he said, "I'm really fascinated by fuel cells, but I think the fuel cells are too complicated. We want to have much simpler fuel cells." And he thinks, and that's quite some time ago. He said, I want to work on direct methanol fuel cell, because that's the ability to have a simple system and convert this to electricity. And at the time, actually, there was not much work being done. It's about 15 years ago, actually, when this happened. And so he came, actually, and I said, yeah, but I'm not a mechanical engineer, so you have to learn electrochemistry and understand actually the physical principles, because I was also in the physics department at the time. He said, no problem, and but I'm interested in that. And he did actually and then he also said, okay, I want to do business with that. He was very determined from the very beginning. I want to have a company that makes direct methanol fuel cells. So he did his PhD, and even towards the end of his PhD already, he was talking with people from venture capital to provide the money actually for his company. And so this way, by being determined, this is what he wanted to do. He was very clearly knew what he wanted to do. And this drove him actually to, as soon as he was finished with his PhD thesis, he had his company formed, he had the investment money, and this was the first company in the world that produced actually direct methanol fuel cells. Then later they sort of advanced, then they kicked them out because that's the usual way in companies that are sort of founded by scientists. They have an idea for the company, but they have a lot of good ideas, but they are not good business people. So then the business people move in, and then they kick out the scientists, and then And then he formed a new company and sort of got going this way. But he was very successful actually in developing this idea, and I think he also made actually some money with that, because eventually then he sold. They transformed this into a public company, so they sold shares. It was not privately owned anymore, and I think he made some considerable money with that. Yeah. And again, it's determination, right? So you know what you want to do, and that drives you, and that actually makes you successful in the end. That you're convinced actually of a certain concept, and then you overcome all kind of difficulties and barriers that may be in your way. Difficulties are good for being overcome. Problems are good for being solved. Yeah?
I'm very glad to be here to take this lesson. But what if you are failed in the research that you are very interested and people and the problem is unsolved after a couple decades? Will you regret?
If I would regret sort of what I've
failed in your research
You-
after a couple decades, will you regret?
so you mean
You have the interest and you
Yeah.
you have the curiosity and you have a strong relation.
so why? No, I didn't quite understand. Why should I regret this actually?
So will you be regretful if after 10 years of effort, but you still haven't solved the problem?
Oh, you haven't solved the problem. No, I mean, yeah, okay, maybe at some point you have to change then your direction. I mean, you have to be critical about yourself also. I mean, you have the problem, and then you have to ask, how do I solve the problem? And you take a certain approach in solving the problem, right? And when you have the feeling that's not going to be successful, then I have to take actually maybe a different approach in solving the problem. So I have to be flexible about my approach in solving the problem. Yeah, and only if I have actually used different approaches and still feel I haven't been able to solve the problem, maybe then I have to reconsider if the problem is maybe too difficult to solve, and maybe I have to switch to another problem. But in terms of research, the question actually of success in the community is also that you identify problems that people think are important problems. So when you actually come up with some solution, then they say, okay, that was a good way. Actually, like your professor, right? She has applied maybe mass spectrometry and IR spectroscopy simultaneously to a certain problem, and that reveals certain things other people have not been able to by looking only at spectroscopy. Yeah? So that's combining techniques in solving a scientific problem is actually something that's good, even if you have not solved the problem completely. But you have shown that with a combined approach, I can understand more than with a simple approach. So there are many sides to it. It's not only to solve the problem, but then also actually develop techniques that allows you to solve the problem. And let me give you another example. It's actually a negative example. We have started actually ourselves a long time ago to say, okay, the temperature range in a liquid electrochemistry is relatively narrow. Let's go actually to a wider temperature range to evaluate kinetic parameters and go to lower temperatures, freeze actually electrolyte, because we have shown that you can do electrochemical measurements at very low temperatures also. And we have done this actually for, I think, almost 10 years or so, this work.